we're going to look at basic probability on, well, basic should be a review, a little bit of probability for you. The probability, it only has basic probability at the top of your worksheet 5. Okay, this is on your 5A. You do not have all this written down. So what I'd like you to write down is the word theoretical. Theoretical probabilities is, and you can abbreviate this, the number of favorable outcomes divided by the number of possible outcomes. Now, an example of spinning a spinner with the entire alphabet on it. I'm making something up. Spin a spinner. Do you need a packet? Spinning a spinner. Getting a C. And it's got the whole alphabet on it. That'd be 1 out of 26, theoretically. Okay? That's a theoretical probability. You're thinking that every letter has an equal chance of getting picked, right? Experimental, though, has to do with the trial. So all you need to write down for experimental, the number of times the event occurred, given the number of trials that were performed. They're just a little different. One's based on an actual experiment, one's based on what in theory should happen. Guys, we need to be working on our notes. What's the probability of choosing a girl from the students in our class? Well, I would have to count how many girls are in here right now, and don't count, not counting myself, we're just talking about students. That's 1, 2, 3, 4, 5, 7 girls. Out of how many kids? How many are in here right now? Just right now. 18. Aren't there 18?
Yeah.
Okay. Now there's some people absent today. So the probability of a student being a girl in our room today is 7 out of 18. That's basic probability. Now, deck of cards. I have found that a lot of students aren't familiar with decks of cards, so I'm going to show you a deck. Okay, there's a deck of cards. A deck of cards has 4 suits. Each suit has 13 cards in it. So there are a total of 52 cards in a deck. There are 13 clubs, 13 spades. That's the second row. Those are both black. There are 13 hearts. You can tell which ones are the hearts, I hope. And you can tell easily which ones are, there are 13 diamonds. So if you've never you haven't played cards. I played a lot of cards when I was a kid. There are 1 through 10, and then the face cards, Jack, Queen, and King. So what's the probability of getting a red card? Well, half of them are red, right? Or 26 out of 52. 2 suits of red, 13 each, 26 out of 52, or 1/2. You want to reduce your probability. Probability of getting a heart. Well, there's only 1 suit out of 4 that gives you a heart. So it should be 13 out of 52, which is 1/4. Probability of getting a red 7. How many red 7s are there? Yep, there are 2 out of 52. So that gets reduced to 1 out of 26. And the probability of having a black heart. No chance. None of us here have a black heart. Kind of a joke in there, guys. Here's another view of a set of cards. Lots of cards are a little bit differently designed. And here's another pair where they're just kind of lined up showing the top number. Those look like the kinds I've used a lot. I think, what are they called? Does anybody know them? Never mind. Oh, there's a certain brand of cards. Bicycle, yeah. Rolling a dice. The sample space for rolling a dice is 1, 2, 3, 4, 5, or 6. The probability of rolling a 4, 1 out of 6. How many of those numbers are even? Probability of even would be 3 out of 6 or 1/2. Probability of rolling a number bigger than 1, well, 5 out of 6. And the probability of rolling a 7, you're not going to get one. Unless you have a pair of dice. Okay. A pair. Pair of dice, yeah. All right. You have Bob instead of Ann on your paper, I believe. I got to fix this. Now, I'm not going to use abbreviations. I'm just going to write their names because we're going to figure out the combination of our boss is going to choose a team of 2 people to lead the department, and everyone is equally likely to be chosen. Show the possible combinations for the team. You could have Bill and John. Well, I'm going to go kind of in a logical way so I don't make any repeats, okay? Bill and John, Bill and Sue, Bill and Bob. Now I'm done with Bill, so we're going to move on and get John and Sue together. John and Sue. John and Bob. And Bob. It sounds like we're the Waltons. Okay. Now we have Sue Bob. Okay, that's it. Now, if we write any more, guys, I know I'm making some jokes, but we got a lot to do today, so let's keep rolling. Bill and Sue get the promotion how many times out of this group? Only 1 out of how many possibilities? It was 6. We made our sample space. Probability the team is made up of 2 men. 1, 2, 3. Assuming Sue is a female. It is 3 out of 6, which is 1/2. We are making assumptions, right? All right. Bob is one of the people getting the promotion. He's 3 out of 6, which is half of the time. I guess everybody has a chance of 50-50 chance of getting it, right? Except we don't know what that boss is thinking about them. These are, again, theoretical. A couple is planning on having 4 children. Write out the possible outcomes. Remember, birth order would constitute a different outcome. We're going to write these out on another, a little later in the lesson. So I'm going to show you how to do it without writing the whole list. Okay. How many choices do you have for child number 1? How many choices for child number 2? So that so far would have been 4 different ways. How many possibilities for child number 3? And then child number 4. So that actually comes out to 2 to the 4th or 16 possible outcomes. Now, the probability of having all girls. Girl, 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 girl would be 1, 1, 1, 1. Oh, there's actually how many? Well, a total of 1 out of, no, guys, 1 out of 16. There are 16 different combinations of ways to have those children. You have to remember, birth order constitutes a different outcome. So having a boy, then a girl, then a boy and a boy is not the same as having a boy, then a girl, then a boy. That's different. Okay, so I'm going to show you how to get them all in just a little bit. We're going to do a tree diagram to get every possible combination. There are 16 ways for this to come out. So the probability of all girls, though, how many ways can you have just all girls? 1. There's only 1 out of 16 ways to have all girls. The probability of all boys is also 1 chance out of 16 to have that happen. All right, the probability that you have at least 1 boy. Now hold on. At least 1. It's only 1 way you can have all boys. So what's how the rest of them will have at least 1 boy, right? 15 out of 16. Okay, now there's another way to think of that. I'll talk about that in the next page. So probability rules. The probability of an event, A, is denoted by P of A. The probability of any event is a number between 0 and 1. 0 would mean no chance, and 1 would mean 100% chance, or always happening. The closer to 1 the probability is, the more likely the event is. The sum of the probabilities of the outcomes in a sample space must be 1. Add up to 100%. Probability of event not occurring is 1 minus the probability of the event occurring, known as the complement. So if the probability of an event occurring is 3 out of 5, what's the probability that it doesn't happen? Okay, now what that is 1 minus 3/5, which is 5 over 5 minus 3 over 5, which gives you the 2 over 5. All right, now look back here. That was the whole thing. The probability that you don't have any girls, right? The probability of having at least one boy would be the probability of the probability of not having all girls, right? So that's 1 minus 1/16. That's where that comes from. Okay, so next, compound events. If you have independent events that do not affect each other, that's what an independent event is. They don't affect each other. Then you multiply the probability of the first event times the probability of the second event. So if you roll a dice and flip a coin, the probability that you roll a 5 would be 1 out of 6, excuse me. I was thinking of that number. And then you would multiply that times the probability of flipping a tail on a coin, which is 1/2. So the probability of both of these things occurring is 1 in 12. If you roll a pair of dice, what's the probability you roll a pair of 3s? Well, the first dice, you have what's the chance of getting a 3? Second one, multiply it, 1 out of 36. Okay. The chance of you passing a test is 40%. Oh boy. Which means you have a failure chance of 60%. The chance of you, it's a bad scenario, guys. The chance of you passing test B is 20%, which means you're probably going to fail it, but it's going to be an 80% chance of failing it. Note that these are independent of one another, though. Probability if you fail A and fail B. Failing A, 60%, 0.60, times failing B, 0.80. That gives you, when you multiply them, 0.48, which is a 48% chance. Probability of failing A was 60, 0.60. Probability of passing B was 20%, 0.20. Together, you multiply them and you get 0.12, which is 12%. Probability of passing A, 40%, times failing B, 80%. Oh dear. Then you multiply those and you get 0.32, which is 32%. Probability of passing A and passing B doesn't sound good. Passing both is 0.40 times 0.20, which is 0.08, and that's only 8%. But there's still a chance. What is the probability? What do these add up to? Look, 48, 58, 60, 70, 80, 90, 100. So that means you got an A+. Okay, events that are independent and dependent. Now we did independent a moment ago. Now we're going to do dependent events. Multiple events that have an effect on each other. The probability of A and B occurring is the probability of A times the probability of B, given that A already happened. Or the reverse of that, depending on which one does happen or count on the other one. Okay, so this is just the same thing. So we're going to just use it with our head. What's happening first? If you have a deck of cards, what's the probability that you'll pull 2 aces in a row? This is called without replacement. The first ace, you have how many aces in the deck? 4 out of 52 cards. Now, once you pull that first ace, how many aces are left? 3 aces, and how many cards? 51. Now, use your calculator to get this reduced. I think it's 1 and 2, 21. You know you can multiply those and then hit math enter, right? I just reduced them and then multiplied. But it doesn't matter. 4 divided by 52 times 3 divided by 51, math enter. Should be getting 1 and 2, 21. Okay, you have 30 students in your class, 17 are boys and 13 are girls. You need to select a president and a vice president. What's the probability of us having a female president and a female vice president? So females, there are 13 girls for the for the president out of a total of 30 kids. Once you get that first selection for president, how many girls are left to choose from? Yes. Okay, now you want to reduce that. I think I did that. It's at 26 at 145. No, that's 26 out of 145. Right? Or did I not go far enough? No, that's right. Okay. Number 3, union of probabilities. When it says or, okay, that's important. If it says or, the union of probabilities is the probability of A plus the probability of B minus any overlap. Okay, like that's true of both of them, and this will make sense after a couple of examples. So you want to do, if it says A or B occurring, you've got to do the probability of A plus the probability of B minus any overlap. So A and B are said to be mutually exclusive events sometimes, and that's when the probability of A and B equals 0, or it is just the probability of A plus B because there's no overlap. So let me explain by some examples. You'll understand better what that says. From a deck of cards, what's the probability of pulling a red card or a 2? Okay, so how many red cards are there out of 52? How many 2s are there out of 52? 4 out of 52. But wait a minute, how many of those are red 2s? So you would have to take away the overlap. That's what that means. Okay, so there's another way to do it. You don't have to do the formula because you could just think, well, 26 are red. That accounts for 2 of the 2s, and there's 2 black 2s to add on. We should be getting 28 out of 52. And then that reduces, 7/13. Okay, we're going to rolling a die. What's the probability of rolling of 6 or a 3? Now, a 6 is 1 in 6, plus a 3 is a 1 in 6. Is there any overlap? Is a 6 a 3? So they're mutually exclusive of one another, okay? So that's why this is just 2/6 or 1/3. That's what they meant by mutually exclusive events, don't have any overlap. So if it says, what's the probability of rolling a 6 or an even? 1 in 6 for the 6, plus there are 3 evens, 3 and 6 for the evens, but 6 is an even, so you'd have to take that away, 1/6, and you end up with just half. 3/6 is 1/2. Or you could just say in your head, what's the probability of rolling a 6 or an even? 1/6, and then there's 2 other numbers that are even, 3 out of 6. Okay, in a math class, there are 14 seniors, 8 juniors, 5 of the seniors are male, and 4 of the juniors are female. I think it might be good to organize this data a little bit. So what I'm going to do is make a little chart seniors, juniors, and then you got what they're male or female. Okay, so I'm going to organize this data. That's what I need. There are 14 seniors, that's your total, and 8 juniors, okay, which gives me a total of 22 kids. 5 of the seniors are males, which would make 9 of them females. 14 minus 5 is 9. And 4 of the juniors are female. 4 and 4 then. Yeah. Oh, my pen stopped working here. There we go. That's a 4. All right. So then how many males do we have in all? 9. And then you see how we can get a bunch of data now? 9 plus 4 would be 13 females. You got more information by organizing this in a chart. I didn't like how my 4 looked, so I kind of just was wanting to fix it. All right, let's answer the questions now. Probability that you're a senior or male. Now, here's 2 ways to go about this problem. We can follow the formula for the OR, which is the probability of a senior, 14 out of 22, plus probability of being male, 9 out of 22. And then I'd have to take out the overlap of seniors that are male, 5 out of 22, and then I could get the answer. Or you can go and say, there are 14 seniors, and then how many more guys are there besides those 14 that are juniors and they're guys, males? 4. So we should be getting 18 out of 22. This, what? 23, this would be 23 minus 5. It is 18 out of 22. I don't care which way you get the answer. You can use the common sense or you can do the formula. What's the matter? Okay, let's do this one. Probability of junior or a female. If you're, how many juniors are there? All right, you can do 8 out of 22. How many are females? Wait, no. How many are all females? All of them, 13 out of 22. But how many are junior females? All right, you'd have to take away 4 of those. Now, otherwise, you could say, well, how many are female and junior? Oh, how many females are there? There are 13 females. And, or no, sorry, there are 8 juniors. And then there are 9 more females that are seniors. You should be getting 17 out of 22. And it works either way. Okay. Yes? Colton? Oh. Okay. And the last one, probability junior or senior. Okay. They're all juniors or seniors. Your doctor's going over statistics of a risky operation. The surgery has a 25% failure rate, which means it has a, yeah, I like the success odds better. If the surgery works, then there's still a 17% chance of infection, so 83% no infection. The surgery can fail, and you will still get an infection 3% of the time. Ooh. Well, that'd be a bummer. Surgery didn't go well, and you got an infection. Oh, double whammy. What are your chances of a successful infection-free surgery? So it's successful, which is 75%, right? And then infection-free. So you get a 17%, if it works, you have a 17% chance of infection. We need to look at this one, okay, because it didn't fail, right? You have a 17% chance of getting an infection, and it says you want it to be infection-free. So we're going to multiply it 75% times 83%. All right, and that gives you 62.25%. You multiply 75% times 83%. Okay, statistics show that if you just buy pants without trying them on, you have a 30% chance of them being too tight, which means they don't fit, and a 10% chance of them being too loose. So what's the total percent chance they do not fit you? 40% chance no fit. Okay, what's the probability of you purchasing pants that actually fit you without trying them on? Yeah. Okay, to meet state standards, Harlem does research and discovers that 80% of the students need help with math, 70% of the students need help with English, and 55% of the students need help with both. Now, I could do a Venn diagram for this. You ever seen one of those? 55% need both math and English help. 80% of them need help with math. So 50, what's 80 minus 55? Yeah, so that'd be 25% there. And then English was 70% total, so this would be 15%. So what's the probability you need help with math or English? I don't know if this Venn diagram helps me. I like to just do it with need help with math or English. So I'm going to do math is, what was it, 80%? Plus percent chance you need help with English was 70, but you have to subtract the overlap. So 80% plus 70% minus 55% is 95%. Do you see how you could get it off the Venn diagram? Look, add these. 25, 55, and 15. All right. Conditional probability is next. The probability of an event happening, given the fact that another event has already occurred. Okay. It's the probability of A given B has happened. Probability of A and B divided by the probability of, I think that's supposed to be, I think I might have this formula written down wrong. 1 second. What page are we on? A still? Okay. 6A. Yeah, this is supposed to, oh, I corrected it. Good. It is supposed to be B. All right. I just like looking at the chart and thinking about it. What's the probability you're an independent worker? 17 out of a total of how many people? 140. Okay. What's the probability that you're a production worker? So you got to go sideways. 92 out of 140. Oh, that reduces though. 23 out of 35. Divide by 4. Probability you're independent or a production worker. Now, we could use the formula that we've been using with that overlap stuff. Independent or a production worker. Well, there's 17 out of 140 that were independent. Plus there are 90, well, let's do with the 140. So our denominators match. See what I'm saying? I'm not going to use the reduced form just because I want my denominators to be common. 92 out of 140 for production worker, but we have to subtract any workers that are both production and independent, which is 8. So I got to take out that 8 out of 140. And I get my final answer of 101 out of 140. Oh, good question. I think it is. Some of the digits doesn't do anything for me. Yeah. Yeah. executive given you're a Republican. Now, you're given that you are a Republican. This does not say or, like this one did. Executive given you're a Republican. So you want to look at only Republicans. And how many of them are executives? 34 out of 55. So you have to be a Republican, and you just do this with logic. Probably you're independent given you're a production worker. So now we're only looking at production workers. And you're an independent as well. So that's only 8 independents out of a total of 92 production workers. That reduces. I think those are both divisible by 4. Yeah. 4 and 23. 2 and 23. Now, counting trees. Counting techniques. Tree diagrams. Maybe you've heard of a tree diagram. You're going to put a coin and roll a dice. We're going to put down all the possible outcomes by a tree diagram. So what's the first, what can happen if you flip a coin? Heads or tails? Okay, now, if you roll a dice next, what are the choices? You get a head and a 1, a head and a 2, a head and a 3, a head and a 4, a head and a 5, or a head and a 6. Then you can go to the other side and get a 1, a tail and a 1, tail and a 2, tail and a 3, tail and a 4, etc. This is a tree diagram, and I made mine a little bit unique. I couldn't help myself last hour and think of this thing as being some kind of a big bug with wings. And then it reminded me of the one, no, sorry. There's our tree space. How many possible outcomes are there in all? Anthony. All right, in a class of 30 students, they have to choose a president, a vice president, and a secretary. And a student can hold only one position, all right? That's usually the case, right? How many different outcomes are possible? This is called counting principle. So given that every kid has the same chance, how many kids do you have to choose from for the president? How many do you have to choose for the vice president? And after that's picked, how many do you have to choose for the secretary? That's it. And you got to multiply these babies. It's a rather large number. Matter of fact, I think I forgot to even write down the answer to that question. It is a lot. So will you tell me? Melanie? 24,000. Okay, 24,360 different ways. We're going to revisit the baby or having 4 children problem. We're going to create a tree diagram that shows the possible outcomes. Okay, do you really want it to look like a tree? So should I do it kind of like I did the butterfly one? Oh my gosh. All right, let's say what do you have first? A girl or a boy? Girl, I heard girl. All right, girl power, here we go. The next child could be a girl or a boy. The next child could be a girl or a boy. And it could be a girl or a boy down here. That's only for 3 kids. Let's keep going. We could also have another girl or a boy for our 4th child. What, Max? Now, what if our first child hadn't been a girl? It happened to be a boy. Then you could have had a girl after that or a boy. And then from there, you could have a girl or a boy. Yep. And then you could have a girl or a boy. The same number as it was before. What was it before? You count the last row. 1, 2, 3, 4, 5, 6. No, you don't. How many are there? There's, look at, on the branches. 1, 2, 3, 4, 5, 6, 7, 8. And there's 8 more over here. So there's a total of 16 possible ways. They could still be boy or girl. Yeah, you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 6, 8 going that way. Okay, now the number of branches does reflect at the very end if you extended these. That's 8 and 8. Now you could get any of the combinations. Like you could decide how many different ways could you get 2 boys, how many different ways could you get 3 girls and a boy. Okay, there's different numbers within that. This sample space is important to know if you were answering more complicated questions than just the ones we did where it said how many ways can you have all girls. Well, that's just one way out of the 16. How many ways all boys? One way out of the rest of them have at least one boy, right? The only one that doesn't have a boy in it is this one. So that way that was 15 out of 16. But you could go for more complicated questions using this now. How many possible combinations are there? We already did it, 16. Okay, just a few minutes on permutations and combinations. You can actually do your assignment though without having these formulas. So what I want you to realize before, I'm probably going to wait till tomorrow because I had to in my other class as well. So I'm going to go ahead and continue this tomorrow. What your assignment is to do page 10 through 11. It's a P, a capital P. Okay, hold on one second. It says at the bottom of this page, right? Or where is it? On 8, I think it's your worksheet 8 where it says 0.04, the counting principle. Okay, I'm going to come back to the permutations and combinations. Right now I want to look at this page. This is your 8, right? We're going to do a few examples here. We've already kind of looked at this idea within some of the questions we did today. The other part of the assignment is on the board back there, worksheet 9 you want to work on. All right, so before we do that, let's do some examples on the counting principle. There's a lunch special today. You can choose 1 out of 3 entrees available, 1 out of 3 side dishes available, and 1 out of 4 drinks available. How many different meal choices are there? Well, how many choices do you have for an entree? 3. How many choices for a side? 3. How many choices for drinks? 4. So you multiply those possibilities to get the total number of meal combinations that you can come up with. That's 36. Okay. To make your own adventure story lets you choose 6 starting points, 6 times 4 plot choices times 5 possible endings. This is called the counting principle. So that would be 6 times 20 would be 120 different adventures. A password has 4 letters followed by 1 digit. Uppercase letters and lowercase letters may be used and are considered different. There are 26 letters in the alphabet. So if I double that, that's, did you think about a deck of cards in an alphabet? There are 52 choices for the first letter. You're going to have 4 letters. It says how many passwords are there? All right, 4 letters followed by 1 digit. 52 times 52 times 52. I guess you can repeat. They didn't say you couldn't, you didn't, weren't able to repeat the letters, so I am not worrying about that. And then wait a minute, how many digits are there? Yeah, 0 counts as a digit, so there actually are 10. I don't know if I'd want to use O's and zeros, though, but anyway, they're 10 digits. 0. Okay, this is really magnificently large. So it's 73,116,160. How many ways can you use? That's why we have lots of ways we can make license plates. How many ways can you use? Listen to 3 songs from a CD that has 12 selections. Now, careful. Your first selection, you have 12. But you already listened to that song, so now you would have to think about that, because the next one then would be 11 and then 10. So you can listen to those. Oh my gosh, let's see, you only have 12 selections. You still got 1,320 ways to listen to them, 3 at a time. And your outfits. Members of 6 different school organizations decorated floats for the homecoming parade. How many different ways can first, second, and third be awarded? 6 different schools. First place. You're not going to take second if you already got first, so that would be how many schools left. And then 4. Oops, my pen just stopped writing. There we go. So that's going to be 120 ways. And then last but not least, you have 3 blouses, 3 jackets, and 2 skirts. Assuming that they aren't clashing in color, how many outfits can you make? You got what I'm saying? 3 times 3 times 2. That's 18 outfits. Okay, you are ammunitioned to be able to do your assignment. So you want to do this and worksheet 9. Have a great evening. I made lasagna.